Hello, everyone, and welcome to episode 34 of Diabetics Diabetics Radio. I am your host, Bowie. Today's episode is titled, Why Serum Ferritin Isn't a Reliable Metric for Iron. We're going to look at the historical acceptance of serum ferritin as the go-to blood metric for our iron load, why it isn't as clear as we've been told, some of the things that we've learned along the way that have muddied how good of a marker it is for iron load. And we'll talk more about some of the better ways to piece together our body's true iron status. Now, if we have not met, my name is Bowie. I have had type 1 diabetes for over 22 years. I, about 2 years ago, set off into the research, reading on my own, taking bits and pieces from everything and piecing together a more comprehensive picture, because as anyone with diabetes knows, the outlook with what we're doing right now is not enough. And so I decided to kind of branch out on my own and start implementing things on my own, and I have had nothing but success along the way. I have created community of those also interested in exploring alternative means of healing, and it has become everything you see here. I've got a TikTok as well, at Bowie_Madison. Go ahead, subscribe here to the Diabetics Diabetics page. We talk about research papers, everything new in diabetes treatment. So let's go ahead and get started. So what we're going to look at is our current iron standards, right? Whenever I talk about iron, most people always think, if they know anything about their iron load, they're like, oh, well, that doesn't apply to me because I have low iron. I'll ask, well, how do you know that? Well, my serum ferritin tests always come back lower than expected. So, our judgment of what's high and low is all based off of what was accepted back in the 70s. And we'll talk more about how we got there, the history of ferritin as a blood metric. We're going to recap some of the important parts of our body related to transporting iron with the body, storing iron in the body. And then we'll explore some new scientific findings regarding the implications of serum ferritin and how it's not so cut and dry in terms of what serum ferritin means. And we're going to look at some of the other things, other markers in our body that give a more comprehensive, all-encompassing picture of what our true body iron load is. Now, let's talk about what serum ferritin means to the general public right now and to the medical community. So, serum ferritin is the current industry standard for a snapshot of your body's iron status. So, if you've ever gotten a blood test done and gotten your serum ferritin levels back, usually when you get your level, it will also be accompanied by an acceptable level, right? We want to fall within a certain range. The range for serum ferritin is a relatively large range, anywhere from 30 to 300 nanograms per deciliter. And the way we see it now, if your ferritin is high, ferritin is a iron binding, iron neutralizing protein, typically reserved for storing iron. We'll expand on that later. But if you have a lot of ferritin, which is meant to store iron, in your blood, that means that you have a lot of iron. If you do not have a lot of ferritin in your blood, that means you do not have a lot of iron. And so that's kind of the logic we've been using. We've been using ferritin as that gauge of what our iron status is. So the beginning signs of hemochromatosis, which is hereditary iron overload. If your ferritin levels are over 500, that's when people start to care about what your iron status is. They'll put you on chelation therapy. They'll recommend phlebotomy or donating blood. Low ferritin, is typically anything less than 15 If you're less than 15, chances are you're experiencing symptoms of anemia, which is mostly fatigue is usually the main one. And they will begin to supplement iron. So if you're low on iron, the logic goes, well, if you're low, we've got to give you more. It's not now. Serum ferritin isn't the only metric being used. Serum iron is the other most common measure of iron status. Serum iron is measuring how much iron is bound to transferrin in your blood. Now, if this all is brand new to you, I've talked about this before in earlier episodes of the podcast. There are 4 major iron chaperone proteins. This is not a comprehensive list. These are the ones that people are talking about the most. So, for starters, the prefix fer, F-E-R or F-E-R-R, is related to iron. Okay, so if you see F-E-R, ferritin, anything fer, that has to do with iron. So ferritin, iron in, storage inside the cell. That's typically what ferritin is meant for. It is an intracellular protein responsible for packaging iron and saving it for later, or making sure it's neutralized within the cell. Transferrin, transport iron, transfer, means it's basically a taxi for iron throughout the body. Transferrin is the go-to transporter responsible for getting iron other places outside of the cell. So it moves iron throughout the body. Ferroportin, portal for iron. This is a transmembrane protein, right? So it spans the membrane of cells and allows iron to move in and out, right? It's a gateway. Hepcidin is the master iron regulator protein, okay? So this is the protein calling the shots from within the cell. It's responsible for orchestrating changes in cellular iron load. So it has a direct impact on the amount of ferroportin in the cell, in times of inflammation, in times of iron deficiency. Hepcidin is the one calling the shots, making sure that the cell has enough iron and that the iron is being transported appropriately once it's been absorbed or if it needs to be mobilized. Now, what most people don't know is that transferrin is, by and large, the number one preferred chaperone protein for transporting iron. People see serum ferritin, they associate it with, if it's high, if ferritin's high, iron's high, if it's low, iron's low. They think that ferritin is a transport protein and that it is able to, but that's not its main job. Transferin's job is to do that. Now, another confusing aspect of that is that transferrin doesn't technically hold as much per molecule as ferritin. Ferritin can hold a lot of iron, like thousands of molecules of iron. Transferrin can only handle 2. However, the volume of transferrin is significantly high. So what it does not have in the quality of iron holding, it makes up for in quantity. It is also more magnetic in terms of having a higher affinity and a preferred binding for any free iron that is circulating in the blood. And there are some ties to transferrin levels and disease states or states of inflammation. Now, there is some ambiguity in all of this. There are situations where this isn't true all the time. That's why I said typically with these, but in states of iron deficiency, where there is not enough iron, transferrin will increase, which makes sense because think of it like a taxi in a city, right? If you are walking through the city and there's like taxi drivers looking to drive people someplace, like business isn't good, and they've got, we've got a lot of feet on the ground wanting to kind of mobilize people and get people moving. Now, in a decreased or in a disease state, there is less transferrin in states of overload because, and this may be a little counterintuitive at face value, in states of iron overload, all of the iron is being locked inside the cell. So there are fewer people in the city, right? Less people. If there are just, fewer people in a city, a less populated city, the number of taxis present is going to be significantly lower, right? So in those states of disease where iron is being stowed away, less transferrin. So now let's talk about how serum ferritin came to be the accepted metric for iron load, okay? And it really, there really isn't this really long story to this. I'll try to keep this brief, but this is there's like one or two papers of this group of researchers who were responsible for, or who were interested in finding the ties between, finding a good metric for iron load, right? How can we tell if someone is high or low in iron? They happened upon ferritin. So this 1972 paper, Ferritin in the Serum of Normal Subjects in Patients with Iron Deficiency and Iron Overload. This paper found a correlation of serum ferritin levels with iron disorders. Okay, the two main iron disorders are iron deficient anemia, which is too little iron, and hereditary hemochromatosis, which is too much. So they took a big group of people, those with anemia, those with no documented iron disorders, and those with hereditary hemochromatosis. And they took everyone's serum ferritin levels and found that those that had anemia had low ferritin. They found that those that had iron overload had high ferritin. And then those that had no documented iron disorder was anywhere in between. Okay. And that's basically it. That's kind of like the test that set in motion the accepted standards of, what our iron load is. They did do a follow-up paper 3 years later, where they were like, yep, looks like serum ferritin is useful and a convenient method of assessing iron storage based on our understanding of hemochromatosis, anemia. They didn't really do any more diving into the exact role of ferritin in each of those diseases. It was just kind of a convenient correlation, and so it was accepted. Now, since then, and this is one of the things that really blew my mind, we still, in the year it's 2024 now, in the year 2024, there is still a lot of ambiguity on exactly how ferritin works and the breadth of how extensive its influences are. We know very little about ferritin still. So there has been research on it, none of it particularly conclusive. So there have been discrepancies in the form and function of serum ferritin versus cellular ferritin, right? Like we mentioned before, ferritin is meant to be inside the cell. The characteristics of what's inside the cell and what's circulating in the serum are different. They've also found a relationship with inflammatory status and how those experiencing chronic inflammation, the role of ferritin is changing. And they're still unsure if ferritin is coming upstream of that inflammation and causing it, or if it's downstream and that the inflammation is influencing how the ferritin is being used. Now, it's still inconclusive as to how ferritin gets out of the cell, right? It's supposed to be inside. How is it getting outside? Not sure. Still not sure. And then, like I mentioned before, we really don't understand how extensive the impacts of ferritin are in cell physiology, our immune response, DNA replication. Iron is an important molecule. We don't know anything about the chaperones that are making sure that iron gets to where it's supposed to go. So, something is not quite right? If ferritin is an inside the cell protein, why is it in the serum? And why do we act like the fact that we don't know that is not important when we're using the outside ferritin as a marker of health? That doesn't make a whole lot of sense. And then how might iron's relationship with inflammation alter its serum tissue balance? Does inflammation affect ferritin, or does ferritin affect inflammation, and how does that change? And then in states of iron overload, of which I have kind of focused on in terms of its role in the development of diabetes, if iron excess in the cell is what's dangerous in causing this inflammation, how do we actually know that a cell is overloaded, right? Do we have a good metric to find out what the cellular status is of its iron content and the quality of its iron content? Is the iron in the cell bound to ferritin, or is it not? That is a critical point, because if iron isn't bound to ferritin, that's what's dangerous. And that's what we need to know. And then any updates, right? The world continues, the medical world continues, and it's just, oh yeah, serum ferritin, serum ferritin, serum ferritin. And none of the modalities that we're using to address it are actually helpful. Health continues to decline, iron status continues to be ambiguous, and we're acting like everything's okay. So I love this picture. What is ferritin doing outside the cell, right? You see a sofa at the curb and you're like, technically, yes, it's allowed to be outside, but it's definitely not supposed to be outside. And everyone knows that an outside couch has significantly different characteristics than the inside couch, okay? And we're, here we are trying to pretend like the outside couch is the same as the inside couch. They're not, okay? Ferritin is an intracellular iron storage protein designed to bind and neutralize iron's volatility while it's being stored inside the cell. The molecule itself, and it's not this color, this is colorized, but this is what the molecule looks like, and I think it's pretty cool. It forms like a cage structure, okay? And inside this ferritin molecule, if you can kind of, it looks like you can see through. Inside is where the iron molecules are being kept. Now, one of the most fascinating parts about ferritin is that it is very highly conserved, which means that in just about every single living thing on this planet, from bacteria to plants to mammals and reptiles, everything you look at, it has ferritin or some form of ferritin. It has been around a very, very long time, which speaks to the significance of iron and iron regulation in life, right? Every living thing needs to have a way of managing iron and neutralizing and storing iron. It's important, okay? Now, I mentioned before, transferrin doesn't hold a lot of iron. Ferritin does. Ferritin can store up to 4,500 iron molecules in one ferritin molecule. That's pretty cool. Transferrin can only hold 2. But like I said, the volume of transferrin makes up for that. But every human cell in your body has ferritin. Needs iron to create energy, needs to be able to store and neutralize iron while it's there. Now, when we talk about how iron got outside of the cell, there's a couple different theories on how exactly that happens. There are two extremes on either side of the spectrum, and then there's kind of an intermediate between the two. The first one is that, well, that's just how it's supposed to be. There's a ferritin that can be inside, and there's a ferritin that can be outside. Ferritin can store and neutralize inside the cell, but it can also serve as a transport protein as well. You know, why not? The second, which is on the opposite extreme end, is that ferritin is absolutely not supposed to be outside the cell, and the only way that ferritin can get outside of the cell is for the cell to basically die and expel its contents into circulation. So it's like it's exploded and it's just sending ferritin into circulation, and we're measuring. You know, when we measure serum ferritin, we're measuring the contents of our dead cells and pretending like that's normal. The intermediate, the kind of happy medium between those two extremes is that ferritin is meant to be inside the cell. And in certain physiological conditions, ferritin can be a regulatory protein in reestablishing balance to ensure iron is being managed properly. Okay. Not supposed to be a transport protein, but serves a role outside of the cell that helps it get back to a state where it can be inside the cell. So let's take a look at what the physiological differences are between serum ferritin and ferritin inside the cell. So there was this one paper in 1981 looking at the characteristics of ferritin in those diagnosed with hemochromatosis, right? So think about that for a second. Take this all kind of in the context of these people have too much iron being stored away in their body. Okay, so this is a little bit of a diseased state observation. But what they found was the serum ferritin of those with hereditary hemochromatosis were glycosylated. What that means is that it has a carbohydrate molecule attached to it, which alters its function to some degree. And the altered function was that ferritin stayed in circulation longer. Okay, typically, every molecule protein enzyme has a cycle of being in circulation, either broken down and disposed of, or taken back into the cell to continue the cycle of in and out, up, down, recycled, reused. And glycosylation altered that cycle for ferritin. They also found that the storage capacity of serum ferritin was significantly lower than storage protein. You remember before I mentioned that ferritin can hold 4,500 molecules of iron. This found that it was less than 10%. Less than 10% of that 4,500 was what serum ferritin could hold. So that kind of throws a wrench in the mix of those that are like, oh yeah, ferritin's just a transport protein as well. It's like, it's, for the capacity that it has, it's not holding very much. Something has changed its structure and its function so that it can't hold as much iron. And then they still couldn't quite answer the question as to why ferritin is getting outside of the cell. Then there was another study, this is from 2009, looking at ferritin's role in inflammatory cascades, right? So this is kind of along the lines of ferritin may not be a very good thing outside of the cell. It may be causing things that we don't want it to cause. So this is a call for us to really find a way to get ferritin back inside the cell. So Ferritin functions as a pro-inflammatory cytokine via iron-dependent PKC, NF-kappa B regulated signaling in rat hepatic stellate cells. A lot going on in that title. We're going to talk about all of it. So what the paper found was that serum ferritin levels are elevated with inflammation in chronic liver injury, right? So again, we're looking at a diseased state here, but it's saying that in those experiencing the inflammation associated with liver injury, serum ferritin levels are always elevated. Now, stellate cells, which is a specific type of cell in the liver, are responsible for driving fibrogenesis in response to tissue injury. So fibrogenesis is basically making scar tissue, right? This is a protective measure, right? If our cells keep taking a beating, whether from bacteria, a virus, our own immune system, this is a way to kind of like calcify and kind of like kill off the tissue to prevent any more reaction. So researchers looked at these stellate cells because people with chronic liver injury are experiencing a good amount of this scar tissue generation. Think of, an alcoholic with cirrhosis, or someone with, what's that disease where they turn jaundice? It's not just, their liver doesn't work as well. It's like the tissues are calcifying and the actual structure of the liver is dying. So researchers looked at these stellate cells and found that they had a special receptor for ferritin, and that those increased levels of ferritin were influencing the activation of the stellate cells. So I mentioned before, stellate cells are specifically found in the liver, responsible for the formation of scar tissue, and they are the root of fibrotic tissue in the liver in response to liver damage, okay? Which is something that all diabetics need to be conscious of because of the connections between the liver and the pancreas. Which begs the question, how does this apply to diabetes? So again, remember, context is everything. This paper focused specifically on the facts surrounding chronic liver injury. If you have diabetes, you may be saying to yourself, well, I don't have any trouble with my liver. My doctor never told me my liver may be altered. But entertain for the moment that this is expanding on iron's potential to elicit changes outside of just being a simple marker, right? Or ferritin, that should say. This expands on ferritin's potential for being more than just an iron status symbol, right? And like I mentioned before, because of the ties between liver health and diabetes health, this warrants more attention for our liver health, right? If high ferritin is leading to more calcification and fibrosis in our livers, that is not a good thing. Diabetes or no diabetes, right? And we know that the pancreases of those with diabetes carry more iron. We know that the livers of those with diabetes carry more iron. And there is an association between non-alcoholic fatty liver disease and diabetes as well. So this is not cause for concern, but this warrants more interest on behalf of those with diabetes and those researching. All right, and here's just 2 paper titles. This is not an extensive list. If you were to type in liver health and diabetes, you're going to get a lot of different papers talking about different metrics, tying the 2 together. Common presence of non-transferrin bound iron, NTBI, non-transferrin bound iron, among patients with type 2 diabetes. We're going to talk about NTBI in just a little bit. And then elevated iron indices in patients with diabetes. This is all the way back from 2004 and 2006. We have known about this. The research has known about this. It is not being implemented, and here we are, okay? So I recommend you read these papers. There's a lot more that you can branch off of based on the resources and the citations in those papers. And then, this is kind of like extra credit, but non-transferrin bound iron in hematological patients during chemotherapy and conditioning for autologous stem cell transplantation. So iron has an incredibly important role in cancer development as well. This paper was looking at the rates of NTBI, which is a marker of free iron in the cell, bad iron, the inflammatory iron, during chemotherapy. It was very high. It was very high in those experiencing chemotherapy. It was also very high in those preparing for stem cell transplantation. So all of those cancer treatments and immunomodulating treatments, there's some very suspicious, possibly harmful side effects based on those NTBI levels. So what are we supposed to do about it, right? So, okay, Bowie, iron, clearly not good out of context, right? We definitely need to keep iron in its place. How do we get a better idea, if not serum ferritin, of what our iron status is? So these are 4 of the most common ones. We'll circle back, and there's a couple others as well. But these are 4 of the most direct and give a better picture than just the serum ferritin or serum iron. So they are non-transferrin bound iron, which we just mentioned, NTBI, total iron binding capacity, or TIBC, ceruloplasmin, which is an enzyme that aids in the movement of iron, the safe movement of iron, and then percent transferrin saturation. So NTBI is the term used for the free iron present in plasma. Okay, so this is the circulating iron that is not bound to transferrin, including all the forms of iron present in serum or plasma which are not bound to TF. TF is transferrin, not bound to transferrin and other traditional iron-binding proteins like heme, apoferritin, and hemosiderin, which are just other molecules that bind and neutralize iron in transit. So NTBI is all of the free iron in our serum and plasma, which has the potential to be very dangerous because it is not attached to something to neutralize it. Okay? The more NTBI, the worse off your health. TIBC, total iron binding capacity. Iron binding capacity is the capacity of transferrin to bind with iron, right? How ready, how many empty and available taxis do we have to move iron throughout the body, right? Iron binding capacity is of 2 types: total iron binding capacity and unsaturated iron binding capacity, or UIBC. Now, when iron stores are depleted, transferrin levels increase, right? We talked about taxis in the city. When, we've got people out in the city and you see a lot of taxis moving around, that means the body's like ready to move iron. As only 1/3 of transferrin is saturated with iron in a healthy cell, right? The typical healthy accepted levels of transferrin saturation is somewhere between 20 and 35%. So if it's 20 to 35%, that means 80 to 65% is what we want to be unsaturated. So total iron binding capacity is the total of iron that is bound to transferrin, which we talked about earlier is serum iron, and how much transferrin is not bound to iron, right? So what's our occupied transferrin level and what's our unoccupied transferrin level? So the higher your total iron binding capacity, the better off your health. If you don't have a lot of tools to bind iron, that means there's going to be more unbound iron, the NTBI, and that's not what we want. And then ceruloplasmin, which is just fun to say. It's a peroxidase enzyme, which means it's oxidizing iron, that in humans is the major copper-dependent iron-neutralizing protein in the blood and thus plays a role in iron metabolism. So ceruloplasmin is very closely tied with your body's copper load. Okay? I forget exactly how many molecules of copper is necessary for ceruloplasmin to act, but you need a good amount of copper for ceruloplasmin to do its job. Its job is to transport iron safely throughout the body as well. Okay, it plays a major role in iron recycling. So if you have low ceruloplasmin levels, you can indirectly infer that you have iron that is not being recycled properly, right? And then percent transferrin saturation is the value of serum iron divided by the total iron binding capacity of the available transferrin. So this is how much of the total transferrin that you have available, how much of it is bound to iron. I mentioned before the ideal value is somewhere between 20 and 35%, right? So you want about a fifth to a third of your transferrin bound, which allows for adequate space, the remaining 80 to 65%, to be able to act on any influx of iron to prevent any unnecessarily unbound iron. So let's take a look at the healthy baseline levels. So normal serum iron levels, this is the iron bound to transferrin, about 20 micromolar. Transferrin saturation, like I mentioned, about 20 to 35%. Typical levels of NTBI, that's the bad iron. That's the iron that we want bound. If we have too much NTBI, that means it's out wreaking havoc. We don't want it to exceed 1 micromolar. And that paper talking about the cancer and stem cell transplantation in NTBI, they were anywhere between 1 and 10 micromolar. Not good. Ceruloplasmin, anywhere from 18 to 36 milligrams per deciliter. TIBC, so total iron binding capacity, anywhere from 250 to 425 micrograms per deciliter. Now, 250 to 425, the higher that number, the better. We want our iron binding capacity to be high. That means we have the ability to neutralize any free iron. So the blood test that I have used as my gold standard for my iron status is something called the Full Monty Blood Panel. This is something you're going to have to ask for on special request to your doctor. They are not going to volunteer this. I myself don't even go through my doctor. I order it independently and pay for it on my own. It is worth it, in my humble opinion. So this measures all things related to iron: your hemoglobin, your total iron, your total iron binding capacity, your percent transferrin saturation, your ferritin levels, your transferrin levels, as well as your ceruloplasmin levels. You get all of that information. Very good. It helps to work alongside a practitioner familiar with these levels, which your doctor probably isn't. There are other alternative health practitioners that can help you kind of piece those puzzle pieces together. One thing the Full Monty Blood Panel also does is the supporting minerals helping with iron recycling. Those are your magnesium levels, your copper levels, your vitamin A, zinc, and vitamin D levels. Everything listed there, magnesium through vitamin D, all play a very important role in iron recycling. Okay? Magnesium affects magnesium, vitamin A, vitamin D, all of them essentially are directly tied to erythropoiesis, which is the generation of blood cells, which is one of the main uses of iron, main sites of iron incorporation back into circulation by the body. If any one of these is off, that means there's an inefficiency, an imbalance, something not going right where iron is being incorporated. So if any of those on the right-hand side are off, that means there may be cause for something to accumulate improperly in the iron department. Lots of information. Okay, so that's it for today. We talked about why serum ferritin is accepted the way it is, why there's a lot of information that has muddied that accepted value, all of the things that kind of make serum ferritin not so crystal clear and not such a great metric. We learned about how the iron chaperone proteins work and their relationship with one another, and how we want it to work in the levels that we want them to be at. We learned about NTBI and TIBC and ceruloplasmin and percent transferrin saturation. These are all the metrics we need to get more familiar with if we want to get a better idea of what our true iron load is, because serum ferritin is not cutting it, okay? If you want to know even more about the connections between iron, inflammation, and the development of chronic disease, I wrote a book called An Ironclad Cause, the link for which will be included in the video description. Subscribe to the channel, right? More and more information outside of the current curriculum on diabetes that is going to help you better manage your health, okay? So thank you so much for being here. This is episode 34 of Diabetics for Diabetics Radio. I am your host, Bowie Madison. Thank you so much for being here, and enjoy the rest of your day.